In this video, we're going to take a look at trigonometric functions and their inverses. Trig all starts with this idea of a circle that has a radius of 1, and we're looking at the angle as we move throughout the circle. And this angle theta is going to be related to the arc length, which is the segment of the circle, the segment of the perimeter that angle sweeps out. And the radius of that circle. And so since theta is s over r, we can use that to get equations for the arc length and rework, using the radius and theta. This also brings up the definition of what a radian is. And in trig, and especially in calculus coming up here, we are going to use radians to describe our angles, not degrees, because degrees don't really have much significance. 1 degree is 1/360th of a circle, not all that great. However, a radian is significant in that 1 radian is when the arc length s is equal to the radius. So a radian is the angle at which the arc length of the circle is equal to its radius. Now we know in a circle we have 2 pi radians in the full circle. In that unit circle, if we have a given angle and we draw our triangle from that angle, where this is the radius, the hypotenuse is the radius, then we come up with our 6 trig functions. Now you should be pretty comfortable with these. You should know what these are and how we define them. For instance, sine is the opposite side over the hypotenuse, and cosecant is the hypotenuse over the opposite side. So these 6 trig functions should be in the back of your mind, and you should know how to find them from the basic triangle. Looking at that circle and the triangle on a Cartesian coordinate system, we see that the x is our horizontal, the y is our vertical, and the radius is related to x and y such that r squared is equal to x squared plus y squared, just the definition of a circle. But we can also confirm that through drawing these triangles and using Pythag. And so we see that if we solve for r, it's just a square root of x squared plus y squared. And when we measure these angles, we always want to go in a counterclockwise direction. That is our positive direction. So opening up in the counterclockwise direction, that gives us a positive angle theta. So if we translate those 6 trig functions from the opposite, adjacent, and hypotenuse vernacular to x, y, and r, we can get these 6 definitions right here. Now you should recognize this diagram here from trig. This is the unit circle, and it has all sorts of important information here for us. It has several unique angles, and these are our important reference angles, what we call them a lot of times, where we have pi over 6, pi over 4, pi over 3, and pi over 2. That's all in the first quadrant. Now everything else can be written in terms of those reference angles in all of the other 3 quadrants. So in the second quadrant, this is 2 pi over 3. That's just 2 times pi over 3. And then we have 3 pi over 4. That's just 3 times pi over 4. And 5 pi over 6 is just 5 times pi over 6. And so really the significance to this, 5 pi over 6 is an angle of pi over 6 away from the negative x-axis. And 3 pi over 4 is an angle of pi over 4 away from the negative x-axis. And likewise, 2 pi over 3 is an angle of pi over 3 away from the negative x-axis. And so that is significant in that we see these repeated values for our x's and y values. Now with this unit circle, we get the idea of coterminal angles, such as if we have the angle 8 pi over 3, well, that's starting at the positive x-axis, and we're opening a full 2 pi because 8 over 3 is greater than 2, and then we have a leftover 2/3 pi that opens. So this is actually a coterminal angle with 2 pi over 3. Now what do we mean by coterminal? It means that they actually occupy the same angle in our unit circle. The 8 pi over 3 just has 1 extra rotation before arriving at that final angle. So we know that the point on the circle that's at that angle is -1/2 radical 3 over 2. Now, how do we know that? Well, that comes back to our trig functions, our base trig functions. And you should know, like the back of your hand, the 6 trig functions evaluated at those reference angles. So you need to know what is cosine of pi over 6, what is cosecant of pi over 4, all of those 6 trig functions with those reference angles. If by chance you do not know those, or those are a little rusty, I suggest that you study those, because you will need to have that information readily available to have success when dealing with trig functions in calculus. Now, if we're talking about a negative angle, all that means is we open from the positive x-axis and go in the negative direction. So we go clockwise, and 11 pi over 3, we're going to do one full rotation and then continue on another rotation and stop here at this angle, which if we look at what's the coterminal angle of that, that's simply pi over 3. Now, what's another way we can find that without actually having to graph it? Well, anytime you have an angle that's negative, you can just add 2 pi until it's positive. Or if you have an angle that's positive, you can subtract 2 pi until it gets into the nice range between 2 pi and 0. So 11 pi over 3, if that were positive, we would just subtract 2 pi till we get within that range. But since it's negative, we add 2 pi. So 11 pi over 3, add 2 pi, and we still get a -5 pi over 3. So that's still negative, so we add another 2 pi to that, and then that gives us pi over 3, which is our coterminal angle within that range. With these trig functions, we get all of these unique identities, true statements that we can use to manipulate trigonometric equations or to help us in the algebraic steps. Once again, these are just some things that you need to have memorized. Hopefully you did that in trig. If you didn't, now's the time to do it, because if you don't have this stuff memorized, it's going to be very difficult when we deal with trig functions in calculus. So the reciprocal identities should be pretty simple. That's just defining, sine and cosine, getting the ratio of those two gives us tangent, but then cosecant is the reciprocal of sine, and secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent. Those are pretty basic, and you should know those. Also, with the Pythagorean identities, you should at least have sine squared plus cosine squared of theta is equal to 1. And hopefully you have these other two as well memorized. If not, get those memorized, because we will use those a lot. And some other ones that maybe not be as familiar but will be useful are the double and half angle formulas. This one especially right here, sine of 2 theta is equal to 2 sine theta cosine theta. We will use that a lot, so make sure you know that and understand it. Also, reducing, another way you could call these is the power reduction of sine and cosine squared. We will use those quite a bit in the second half of the semester. Now, these trig functions are periodic in nature, in that they repeat every so often, and so their graphs are repetitive, and they actually go on and on forever as x gets big or as x gets small. And the period of just the base sine, cosine, secant, and cosecant functions is 2 pi. So that means that this cycle will repeat every 2 pi radians. Whereas in tangent and cotangent, the cycle repeats every pi. Now the reason for that, if you want to know why do these two down here repeat every pi, whereas the ones up top repeat every 2 pi? Well, tangent and cotangent actually repeat every 2 pi. It just so happens that they have a repetitive nature within their one cycle, and so it appears as though they'll repeat every pi. And so we see that basically the symmetry within those two functions gives us a more quickly repetitive nature. This here shows you a sine and a cosine graph and the reciprocals, with where we have sine, the reciprocal of that is cosecant. And so, we should be able to graph these and remember what they look like. If you remember the secant and cosecant as the smiley faces and frowny faces, that's fine. But sine and cosine, you should be able to graph, no problem. right away, and then at least from that get secant and cosecant, as well as tangent and cotangent. Tangent and cotangent look very similar. They are reciprocals of each other. One thing to notice here, though, is the asymptotes are different. They are shifted. And that should make sense in that, the asymptotes come about when we have a 0 in the denominator. Well, for tangent, that happens when cosine is equal to 0. Pi over 2, 3 pi over 2, 5 pi over 2, and so on. Whereas for cotangent, that happens when sine is equal to 0. So that's at 0, pi, 2 pi, 3 pi. So you need to understand why they have asymptotic behavior and where they have that asymptotic behavior. Just like any function that we dealt with in algebra, we can shift, stretch, compress, and do all sorts of stuff to these functions by our basic translation rules. So if we have a number out in front of the function, that is our amplitude. That is going to magnify. So if it's greater than 1, it's going to make it bigger. If it's less than 1, it's going to make it smaller and squish it. If it's negative, we're going to flip this about the horizontal axis. Inside, we have that C is going to give us a horizontal shift, whereas B is going to give us a horizontal stretch or compression, and D is going to give us a vertical shift. This is just like any function that we dealt with in algebra. The only difference is that with trig functions, because of their periodic nature, that shift is still going to continue throughout the entire function. One of the things that come up when solving trigonometric functions is, or equations that we have, we can have multiple answers. And so say we have the equation sine of x is equal to 1/2. Well, sine of x is equal to 1/2 an infinite number of times. And so we can't pinpoint it to one specific time. But typically what we try to do is we try to pick the first time that it happens, or when it happens in the first quadrant. So when solving sine of x is equal to 1/2, and basically it's asking at what angle is sine of that angle equal to 1/2, we want the reference angle. So how we would write this is we know that, well, x is going to equal pi over 6, but it's also going to repeat every 2 pi n, where n is an integer. So what is this telling us here? This is telling us that, well, pi over 6 is going to give us 1/2. Sine of pi over 6 is 1/2. And if you didn't know that, you need to review your unit circle. So sine of pi over 6 is 1/2, and that's this dot right here. But also, if we add 2 pi to that pi over 6 and get 13 pi over 6, we also get 1/2. And so that's this dot right here. And we could add another 2 pi to that, and we get this dot here and this dot. And or we could go back to that pi over 6, and let's subtract 2 pi from that and get a negative 11 pi over 6. And that's this dot here and this dot here. And so that's accounting for all of these different points. But if you notice, we're actually missing some dots. We're missing this one, this one, this one, this one, this one. So what's going on there? How are we missing those? Well, this is where we have to remember that in trig, the sine is equal to 1/2 of pi over 6, but that's only one of the two angles where it's equal to 1/2 within one full circle. And so we have to look at our 4 quadrants, and this is where whatever system you want to use, the forecast system, whatever, I don't care what acronym you use to remember it, but you need to remember this right here, in that all trig functions are positive in the first quadrant. Sine and cosecant are positive in the second quadrant. Tangent and cotangent are positive in the third quadrant. And cosine and secant are positive in the fourth. So sine of pi over 6 is equal to 1/2. That's in the first quadrant. Well, there's also an angle in the second quadrant that gives us 1/2 as well. So we need to know, what is that angle in the second quadrant? Well, if pi over 6 is our reference angle, then we have to be up here, pi over 6 above the negative x-axis. So what is that? That's 5 pi over 6 that we get also 1/2. Sine of 5 pi over 6 also gives us 1/2. And that repeats every 2 pi. So that accounts for that angle right there. This process right here of solving a simple equation of sine of x is equal to 1/2, you need to be able to get to this result. Now, more often than not, if it's an application problem or if, depending on the situation, we may just stick with pi over 6 and that's it. We don't need anything else. But if we are just answering the open-ended equation of sine of x is equal to 1/2 and we need an analytical solution, then this whole solution right here has to be present. We have to have pi over 6 plus 2 pi n and 5 pi over 6 plus 2 pi n, where n is an integer. In the last half of this video, I want to take a moment to talk about inverse trig functions. Now, I want to pause here for a second to just remind you that inverse trig can be very difficult to understand at first. But once you get to know it, once you start to understand it a little better, it's not that complicated, but it's not as intuitive as trig functions are at the surface. So let's say we look at the function y equals sine of x, and we're going to restrict the domain to just negative pi over 2 to pi over 2. Now, why we restrict that? Well, that gives us that one-to-one relationship that it passes both the vertical line test and the horizontal line test. Because sine passes the vertical line test for all values of x. However, it doesn't pass the horizontal line test unless we limit its domain. So this is the biggest domain that we can have where we have that one-to-one relationship. So we see the domain is restricted because that's what we set it to be, the negative pi over 2 to pi over 2. And our range is just always restricted in sine and cosine from negative 1 to 1 as long as we're not multiplying by some amplitude. Well, likewise, let's do the same thing with cosine, but we're going to shift it a little bit. If we kept the same domain for cosine, we actually would get a graph that would not pass the horizontal line test. So we need to shift over and say our domain is 0 to pi for cosine, but our range is still the same thing. It's negative 1 to 1. So if we do that, we can find inverses of these functions like we did in algebra. And the inverses of these functions actually become unique functions themselves. And in trig, they just give us a way to undo what we were doing with sine and cosine. But the interesting thing is that they come up in calculus. And in fact, we can relate these to polynomials and rational functions, which is kind of mind-blowing in that they bridge the gap between the trig functions to the realm of the polynomial functions when we start to look at things in the lens of calculus later. So if we say that we have those conditions that we just stated before, and we do the inverse thing where we switch the x and y and we solve, we end up with these two functions. Y is equal to the inverse sine of x, and y is equal to the inverse cosine of x. Now I'm going to pause here for a second to just mention something that's a little bit of a pet peeve of mine. I hate this notation. I think it is stupid because it causes confusion. Because a lot of people, when they hear inverse, they think of multiplicative inverse, and they think the inverse of sine is cosecant. Well, no, that's not correct. Yes, the multiplicative inverse, the reciprocal of sine, is cosecant. And so I don't like this notation because it gives that confusion. It gives that idea that it's 1 over sine. It's not 1 over sine. What I would rather you do is I'd rather you write this as arc sine of x and arc cosine of x, because that's really what it is. And all this is just calculator shorthand. To print less letters on the calculator, they came up with this notation, and it gets used a lot, and it just causes a lot of confusion. So when we talk about these and when we write these, this is arc sine and arc cosine, which is the inverse function of sine, but is not the multiplicative inverse of the function sine of x. One of the unique things about these inverse trig functions, or these arc trig functions, is that we have the same domain and range as what we just stated before, but they're flipped. So what was once our domain, negative pi over 2 to pi over 2, is now our range of y. Y only goes from negative pi over 2 to pi over 2. And that means our x is going to be limited between negative 1 and 1. Same thing for both arc cosine and arc sine, their domain is -1 to 1 because the range of sine and cosine are limited to -1 to 1. And the only difference is for cosine, when we have arc cosine, the range of arc cosine goes from 0 to pi. Now, how do we use these? Well, we use these to find angle measures. So say we have a triangle that has a hypotenuse of 5 and it has a leg of 2, and we want to know, well, what is this angle over here opposite to that leg of 2? Well, we can find the other side using Pythag, so the other side is going to be radical 21, but knowing that angle, we need to use inverse trig functions. Using our right triangle trig properties, we know that sine of theta is equal to 2 over 5 because sine of theta is opposite over hypotenuse. And we can say that cosine theta is radical 21 over 5 and tangent of theta is 2 over radical 21. So to find this angle, we now need to use our arc sine function or arc cosine function or arc tangent function with any of these three equations. And so we could write theta as being arc sine of 2 over 5. Now, here's another point that I'm going to pause to make a little public service announcement. When in my class, when taking my calculus class, this is the final answer and this is how I want you to leave it. I do not want you to type this into a calculator and get a decimal. The reason that I don't is because that gives you an approximate answer. I want the exact answer. When we make approximations too soon, our error propagates throughout problems and it screws us up. So when we get an answer like this, when we're solving with these sometimes nasty functions that don't give us nice numbers, then we need to just leave it as arc sine of 2 over 5. However, if this were 2 over, and let's change this and let's make that 4 instead of 5, if that were a 4, then you could simplify that because the arc sine of 1/2, we know what that is. We know that that's pi over 6 in the first quadrant, and then, that's what we said on a slide earlier. So if you can simplify it, you must simplify it and give me an angle. But if it's a nasty angle like arc sine of 2/5, well then just leave it as arc sine of 2/5. The last thing I want to show you here is just a list of the other arc trig functions: arctangent, arccotangent, arcsecant, arccosecant. And in fact, the three that we are going to use the most are going to be the non-co ones. So we'll use arcsine, arcsecant, and arctangent. Now the reason for that is just basically because it avoids a negative that comes out later in calculus. But those are the three that we're going to see appear the most in our course coming up here in the next semester. So, however, you should still know what all 6 of them are. For every trig function we have an inverse trig function, and you should know its domain and range as listed here in the slide before.